this session we have Carmine and Abate talking about trace relating compiler correctness and secure compilation.
Thank you. So in this talk I will give you some trace-based criteria for correct and secure compilation in a quite general setting where your traces can expose between different observables in the source and target. So we'll start by looking at what we mean by traces properties for this work. And let's say that for most of this talk I won't need any structure over traces. So we can assume just to have an abstract set that we call the set of traces. But of course traces can be values, finite list or streams or of event like input-output events. And I will use this notation to say that a whole program W during its execution with respect to a fixed semantics produces a trace T. To be more concrete, let's say that this fib.io is an interactive program that takes from the environment a natural number n, computes the nth number of the Fibonacci sequence and output the result. If you take finite list to be of input-output event to be your traces, you might observe input 7, output 13, or you might also observe input 3, output 2. Of course, you want to reason about our programs, and we will do it by using predicates over traces, or set of traces that we call trace properties. We say that a program satisfies a trace property if and only if whenever it can produce a trace, then the trace is in the property. And fib.io, for instance, will satisfy never output 42, but violates never output a prime number. So the last piece of notation I need is this down arrow that denotes a compilation chain from source language to a target one. And I'm using colors to distinguish the two languages. But if you're colorblind, don't worry, I will use also letters at some point if it's strictly necessary. So the first criterion we have describes sort of refinement of the behavior of the compiled program with respect to the source one. It basically says that whenever the compiled program can produce a trace, then the same trace can be produced in the source. And we call this CC, or compiler correctness. But since I introduced trace properties, you might want to define compiler correctness in terms of preservation of these trace properties and say that whenever in the source your program satisfies a property, then the same property is satisfied after compilation by wcompile. And it's quite immediate to realize that actually these two criteria are equivalent, but still we would like to look at both of them at the same time. We want CC because for it we know there are quite good proof techniques available in literature. And we want TP for a better understanding of our theorem because it has a very clear description of what is the property that is guaranteed to hold after compilation whenever we know that something is satisfied in the source. Or if you wanted to look at it dually, there's a description of what you should prove on your source program to get pi satisfied after compilation. This is the kind of the key idea of this work. So this is very good, but it's not good enough yet. And to understand why, we can give a look to this theorem that we took from the COMSORT development and slightly adapted to our notation. And it basically says that whenever your compiled program can produce a trace in the target, then there exists a source trace that is produced by the program and is not necessarily the same trace as T. It can be made of a finite prefix of T, M, followed by what in COMSORT is called goes from, that denotes an undefined behavior for the original source program W. And it's clear that this is not an instance of what we call CC, because CC uses only the same trace T. But of course you can immediately generalize CC by requiring in its conclusion the existence of a source trace that is not necessarily the same trace as T, but just related to T. And if you take the relation to be exactly what's in these brackets, you can find this theorem as an instance of CC tilde. And CC tilde is actually the first criterion I want to present today, and it's parameterized by a trace relation that is just a relation between source and target traces. That can be different now. And as I showed you, it can be used to define compiler correctness when you compile from unsafe languages and you have some sort of undefined behavior a la COMSORT, or in case you have some bound on some physical resources. And in general, it works very well when you have any discrepancy between source and target values and observable. That will give you also a discrepancy between source and target traces. But it has a main drawback, and that is it is not explicit. In the sense, for instance, it's not clear what is the target property that is guaranteed to hold after compilation, if we have some information on our source program. And so in what follows, I'll try to make explicit both the guarantees we have after compilation and the source obligation we should discard in our program. To do it, I will extend what we call TP, trace property preservation, with two mappings that denotes a translation of properties from source to the target, this tau tilde, and from target to source, this sigma tilde. The name, because the names are so because tau goes to the target and sigma to the source. And let's see how do we get these two mappings. We will use a bit of math, and the idea is easy. Whenever you have a trace relation, you have two very special mappings between properties that sometimes in literature are called the existential image of the relation and the universal image of the relation. Now the definition is on the slide, but you don't really need, I don't really want you to remember this definition. What I want you to remember is that they are very special in the sense that they form a Galois connection between properties of the source and properties of the target. And the Galois connection is actually the key to show that the three criteria I want to present today are all equivalent. And what's the insight of this equivalence that we call Trinitarian view of compiler correctness? That on one side we will have a criterion that is probably the theorem we want to prove. We will try to prove for our compiler, for which there are quite good proof techniques, hopefully in literature. And on the base of this triangle you have two criteria that talk about preservation of trace properties. And one here, TP tau tilde, will have this description of what are the guarantees, what is the property that is guaranteed after compilation. And on the other side, you will have sigma tilde of pi t, that is the property you should prove to hold on your source program if you want a certain target property to be satisfied after compilation. So if we go back to our example of the theorem we borrowed from Concert, I will be quite informal here, but if you want, you can look at the full math at our paper that will appear at ESOP this year. Tau tilde, the guarantee we have after compilation, will be basically saying us that, okay, as long as your program does not encounter undefined behavior, then you are satisfying the very same property. And that as soon as you encounter undefined behavior, you lose all possible guarantees. So this is kind of what we're expecting. While the source obligation will ask us to show most of the time that our program in the source does not encounter undefined behavior, so it does not go from. And now we're going to kind of naturally generalize all these concepts, all this idea to secure compilation, and we're going to see in which scenario. So let's first fix our scenario. So now we are moving from whole programs to partial programs, and we expect them to interact with some context. For instance, they can call some external library or interact with some external application that are written from a third party that we want to consider untrusted, adversarial. Of course, depending on the context, a program may satisfy or may violate a certain property. For instance, let's go back to our fib.io, and let's assume that our contexts have this very easy shape. They call fib.io on a natural number they take from the environment. They make fib.io compute. They add the natural number to the result, and they output the final result. So in the first context, fib.io will still satisfy this property pi, but in the second it will violate pi. So we have a notion, it's very natural to have a notion of robust satisfaction in this setting. That means that it requires that the program P satisfies a given property in an arbitrary adversarial context. So the notation I'm using is very similar to just satisfaction. It's just that you have an array here that is hiding a universal quantification over context. So we are going to consider, to focus on secure compilation criteria that express preservation of robust satisfaction. And this is particularly interesting, I think, in the case where target contexts are strictly more powerful than source context. And this would be our immediate generalization of what I showed you before. So we have still 3 criteria, and on top you can find what we call RTC tilde, that is basically very close to, formally very similar to what I showed you before. It's just that this time there are some context. So you require that whenever a compiled program can produce a target trace in a target context, then there is a source context in which the program can produce a related trace. And on the base of this, line, you have again 2 criteria that are stated in terms of preservation of robust satisfaction. And the key idea is that this time tau tilde of pi s will represent the guarantee the property that is guaranteed to hold after compilation for a partial program in an arbitrary target context. So we might call it robust guarantee. And on the other side, your sigma tilde of pi t will give you the property you should show hold in an arbitrary source context, and this will give you that after compilation, your partial program will satisfy a target property in an arbitrary target context. Again, the key idea to show the equivalence of these 3 criteria is that tau tilde and sigma tilde, the existential universal image of the relation, are a Galois connection. So of course you can look at something more than just trace properties, because trace properties are predicates of a single run of a single program, and the most you can get is data integrity. You might want to reason on multiple runs of the same program and look at either properties like non-interference and get some data confidentiality, or if you want to reason about, I don't know, program equivalence, you might look at relational level properties that are predicates over multiple runs of multiple programs. And this will be the general picture we have in this work. Color, I don't know if you can see colors, but colors correspond to the colors in the table. And it's basically a generalization of the diagram Marco showed before. And in each box you have the 3 equivalent criteria. I will not go through it. I will focus only on the lowest one, that is about safety properties. So we are going to focus only on the preservation of robust satisfaction of safety properties. And this is quite illustrative because you have a main problem when you restrict your attention to a particular fixed class. And the problem is that you may lose the information that your property belongs to the class. For instance, if you focus on safety properties, when you translate a property from source to the target or from target to source, you will lose probably this information that the property is safety. And I have no time, and it's quite technical to understand why this is crucial and very important when you translate from source to target, but if you want, we can discuss this later. So we had to consider an approximation of the translation into the target. And how do we get it? We get it by composing tau tilde with a closure operator that we call safe, and it's basically the operator that defines the class of safety properties. So from now on, you need a bit of structure on more than on your traces, on your properties. But to help your intuition, you might think that basically you have a notion of finite prefixes for your traces. But there are other ways to define safety properties, and if you want, we can discuss this later as well. So, okay. Let's see why this is a good. What was the pay for this choice? So let's start from the key idea of the equivalence I tried to stress before, of the equivalence of the 3 criteria. That was the Galois connection between source and target properties. And we are now composing with our safe closure operator that will map an arbitrary target property to a safety property. Of course, safety properties are still target properties, and you can go back to arbitrary trace properties. And interestingly now, you can compose the mappings in a proper way and get a new Galois connection between source arbitrary properties and target safety properties. And this will be the key to have three new criteria for preservation of robust safety, and to have them equivalent. So on the base, we will find this new Galois connection, and basically this criterion will have a description of the robust guarantees after compilation that is given by the composition of the closure operator and tau tilde. On the left, you still have that the robust obligation in the source is described by just sigma tilde, but this time you will quantify only over target safety properties. And on top, you have this criterion that is called sometimes RSC tilde. And for this one, we have quite good proof techniques in literature because they focus only on finite prefixes. Here in this formula are denoted by M. And it's saying that whenever you can, whenever in a target context, your compiled program can produce a trace that has as finite prefix M, that is the meaning of this notation with a star, then there exists a source context in which the program can produce a source trace that is in this fancy relation with M, and this fancy relation is just hiding the fact that S is related with a trace that is longer than M. So that with a target trace that has M as prefix. So to conclude, I showed you some trace-based criteria that are parameterized by trace relations, or binary relation between traces, and or property mappings. And this gave us a better understanding of the theorem we proved, or we aim to prove, in terms of guarantees we get after compilation, or obligation we should discard on our source program to get something after compilation. In the paper you can find way more. You can find all the diagrams you want for hyperproperties, relational hyperproperties. You can find, I think, an interesting study about preservation of non-interference through compilation in this setting. And you can find, of course, all the mathematical justifications and a lot of examples, and most of this is formalized in the proof assistant. Thank you.
Okay, we have time for questions. Maybe I can ask something. I didn't quite get how these. You said for the safety property there is this safety operator that is kind of a closure. Can you give maybe an example? What does it do?
So basically, it gives you the smallest safety property that includes the property you started from. Okay, so it's kind of intersection of all safety properties that include the property you're considering, right? And it's kind of if you know a bit of topology, it's the topological closure in a certain way.
No, not really, but I understand.
Okay.
More? Yes.
I don't know if it fits here, but the question is, do you think we can do a similar thing for flow structure, for example? Have you thought about that?
So
Repeat the question, please. If you can do a similar thing, if we can do a similar thing like a Trinitarian view with a full abstraction.
So you like the guarantees after compilation of a full abstraction, and right, this would be very interesting. The point is that, so if you want my personal opinion, is that when you look at full abstraction, you have traces, right? The advantage of full abstraction for me is that you can avoid considering traces, but I don't know if it's an advantage. And well, we have.
No, I mean we. Running short, so.
But yeah, so in a previous work we compared full abstraction with the criterion of the diagram of the previous book. So also with this one. So we have a way to compare full abstraction when you have the same traces. So the same observable events at source and target. And the result was that full abstraction was not implying any of our criteria. So in this setting, it can be a bit different, but it depends probably on how you define observables and what are your traces.
But I think also in a way, I mean, we were obtaining, we were relating in the opposite direction. We were relating full abstraction with some relation, preservation of some relation or hyperproperties, by instantiating to just equality between several traces. So in a way, it was a very point-wise. It wasn't a class of things. It was really a point-wise thing we were preserving. So I don't know. In this setting, maybe you also have some point-wise relation that holds. Not the relational classes and the mappings between classes.
Yeah, the point is that if you think at full abstraction here, it would be still equality and equality, the source.
Yeah.
But yeah, you have equality because you are in the same kind of domain, right? Sure.
Okay, thank you.
Okay, so now we move on to the next talk.